All right, so far in this unit, we've talked about the subatomic particles, the protons, the neutrons, and the electrons. We talked about how protons can't change. If they change, you change the element. We talked about isotopes when neutrons can change. And we've talked a little bit about electrons, okay? And we're really, the rest of this unit, we're not going to talk so much about protons and neutrons anymore. We're going to be talking about electrons, okay? And the reason for that is because the electrons, again, we've talked about this when we talked about nuclear reactions, it's the electrons that change when chemical reactions happen. The atoms don't necessarily change in a chemical reaction. Yes, in nuclear reactions they do. But in a chemical reaction they don't, okay? It's the electrons that move around when an atom absorbs energy, okay? It's the electrons that are configured in an atom that determine how an atom reacts, okay? Most chemical reactions only involve the sharing, transferring of electrons, so that's why we're going to focus mostly on those. Okay, a lot of times, again, we use real fancy words to describe things in science. However, when we talk about the electronic structure of an atom, you're like, oh gosh, all that means is we're simply talking about the number and the configuration of the electrons in an atom and how much energy those atoms have. So the electronic structure of the atom is just how are the electrons organized within that atom. Okay, now where did this come from? Now I don't want to get too deep into this, but in the early 1900s, Albert Einstein did propose a theory called the photoelectric effect, which means that when you shine light on something, a lot of times these different elements give off different colors, okay? They emit visible light when they are heated or put into a flame. And they can use that light to determine what element it is. And so we're going to talk a little bit about light, and we're going to talk about how that relates to elements here. We are going to do a little bit of math. So at this point, you are definitely going to want to have some type of calculator for this class. This is a calculator that I use right here. It's, again, nothing fancy. It works great. And it was like $8 at Walmart. So you definitely will want to have something like this. Sometimes I do use my phone as well, but at the same time, on a test, I'm going to ask you to use a calculator and not your cell phone. And honestly, these are much, much easier to use. So let's talk a little bit about light. Now, again, the fancy term for light is what's called electromagnetic radiation. Okay, that's just a fancy word for when energy travels through space, whether it's visible light or other types of light. To me, just another word for electromagnetic radiation is light. Okay, another way to think about it is it's just energy. Okay, remember, that's the one thing that's not matter. When we talk about what's matter and what's not matter, the one thing we said that wasn't matter was energy. Okay, so electromagnetic radiation is any type of energy that carries energy through space, such as visible light, ultraviolet light, which that's the dangerous ones from the sun. Even when you go to get an x-ray, all of these different types of light or energy travel through space, and they travel in what are called waves, just like the waves of the ocean that go up and down. Okay, and each of these waves contains these tiny little packets of energy that are called photons. Okay, so photons are think of light traveling in a wave up and down, and that light is traveling in a little, almost like a train car. Think of a tiny little train car where once you fit all the people into the train car's full, and you can't fit any more people in it. So what happens? Well, then you go to the next train car, and you keep going. The light fits into these little tiny packets of energy, and these little tiny packets of energy are called photons. Okay, so a photon I think of as the light traveling through the air like this, up and down, and there's these little tiny compartments, almost like these little tiny train cars of energy that these are packed into, and they're really, really small. Now, light moves, as we know, really, really fast. Okay, all types of light, all types of electromagnetic radiation move at the speed of light, which is, we say 3 times 10 to the 8th meters per second. If we write that out, though, that is 300 million meters per second. Okay, that means like a ray of light can travel around the Earth like 7.5 times every second. That's 300 million meters. Light moves really, really fast, okay? Now, outer space is also really, really big. It takes the light from the sun about 8 minutes to get here, which means traveling at 300 million meters per second, the light from the sun still takes about 8 minutes to get to Earth. Okay, now, what are all these different types of energy? They're all different types of what's called the electromagnetic spectrum. So we're going to start at the bottom here. The bottom one down here, the first ones are called radio waves, okay? And radio waves are lots of different things, okay? If you have direct TV or dish network, so if you have satellite TV, that's how the light gets to your house, is via a radio wave. Obviously, if you listen to the FM or the AM radio, that also travels as a radio wave. Probably the more common one, though, is your cell phone. Okay, cell phones are within this radio wave spectrum as well. They're very, very low energy waves. They're traveling through the air all the time. When you talk to someone in another city, that your voice gets turned into a digital print, basically, and then it travels via a radio wave to a cell phone tower, and then to another cell phone tower, and goes to the person that you're talking to. And how fast does it travel to them? Oh, it travels at the speed of light, 300 million, 3 times 10 to the 8th meters per second. And that's why you can have a conversation with someone in Florida, and there's a slight delay, but again, when it's traveling at 300 million meters per second, it gets to Florida pretty quickly. Okay, and then you have above the radio waves, you have what are called microwaves, which is interesting because a microwave itself does not use microwaves to heat up your food. I know. Okay, and then you've got what are called infrared. Sometimes we just call them IR. When I think of those, I think of like lasers. A laser, those red lights. That is infrared light. And then this little tiny section here in the middle is what's called visible light. All of the colors that we can see, there's the whole spectrum right there, fall into this tiny little, just from here to here, this tiny little portion of the electromagnetic spectrum. And then as soon as you get above visible light, then you get to UV light. Again, that's what burns your skin. That's a sunburn when you get too much ultraviolet light. Now we're starting to get into the more dangerous ones, X-rays. You'll notice that the person leaves the room when they do the X-ray because they don't want to get hit with the X-rays. And then the real bad ones are what are called gamma rays. Okay, and as you go up this list, the energy also increases. Okay, so gamma rays are really high energy waves that if they hit you, again, you don't really feel it. Just like when you're getting a sunburn, you don't really feel it until later on that day when you're like, oh man, I got a bad sunburn. Gamma rays are the same way, that you can be sitting there watching a nuclear reactor meltdown like happened in the 1980s in the Ukraine. When Chernobyl, there was a nuclear meltdown there, and people were watching it. And these people were getting blasted by these gamma rays and didn't even realize it. The firefighters going to fight the fire that was happening, they got blasted by these gamma rays. And even to this day, these gamma rays, the clothing that the firefighters were wearing are still in the basement at the hospital where they took them, and they are still giving radiation off at this point. I think I talked about that in an earlier video. Okay? So, gamma rays, really high energy. Down here at the bottom, radio waves, really low energy. Okay? Now, again, we talked about how these different waves, how these different types of electromagnetic radiation travel. Okay? And there's two things that we want to focus on when we talk about the differences in these waves. One of them is how big the wave is, or what we refer to as the wavelength. Okay, now wavelength, again, this is kind of a weird symbol. It's actually a Greek letter. It's the Greek letter lambda, okay, Lambda, and it kind of looks like a backwards H. There was a video game a long time ago called Half-Life that used that symbol as to represent its game. It was a really fun game. Okay, Now, what is the wavelength? The wavelength is just how long the wave is. How long, what's the distance between the beginning of one wave and the end of that wave? Okay, the fancy way, it's the distance between two repeating points on a wave measured in meters. Okay, really, it's just how long is that wave? Is it this long? Is it this long? Is it this long? Or is it so tiny you couldn't even see it between my fingers? Okay, waves can be really, really big. They can be measured in kilometers. Okay, and these bottom ones are that. Okay, the radio waves are really, really big waves. Okay, you can see here 100 meters, 10 meters, 100 kilometers, 100 megameters, which is 1,000,000 meters. Okay, they can be really, really big waves. And the bigger they are, again, you can see, remember the energy goes up as you go up. The smaller these waves are, you get to really, really small waves. Those are the really, really high energy ones. So if the wavelength is really, really big, then we know that the energy of those waves is really, really small. Okay? Once you get into the smaller ones, you get to X-rays and gamma rays. Those are really, really short waves. And again, those are, so small that you can't even see it between my fingers there. Okay? So wavelength, the letter lambda with a backwards looking H, is how big, how long that wave is. Okay, the other thing, there's only two things we need to know about the waves, is the other thing is what's called the frequency. Okay, and again, why don't they just use the letter F? I don't make this stuff up, I don't know. Okay, but it looks like a V. Again, it's actually a Greek letter mu, but if you just want to call it a V, that's perfectly fine. Okay, now frequency is a little bit more tricky, in that frequency is, let's say I could see these waves, okay? You can't, but if you could, let's say every time, like I'm looking at the wave right now, and I see one go by and I count it. And I say, oh, there's one wave. And then I count another one, there's two, and there's three, and there's four, and there's five. Okay, that's what frequency is. Frequency is, if you were counting the waves, it's the number of complete waves that would pass by a certain point each second. Okay, now, obviously they're traveling. Remember, these things are traveling at the speed of light. There's no way you could count them because they move so fast that you would have to be able to count really, really quickly to be able to measure these things. So it's the number of waves. If you could count the waves, it's the number of waves that would pass by a point every second. Now, typically the way that we write that is we just write a number over seconds. Or another way to write it is that seconds with a -1. And I don't know if you remember from math or not, but anytime you have something that's to the -1, what it really means is it goes on the bottom. So if you have 25s to the -1, what that really means is you have 25 over seconds, which is what is written right here. Okay? And so many times you will see it written like that. No, and so if you have 25 per second, that means that 25 waves would pass by every second. Now, normally it's a much, much bigger than that because remember, they're traveling at the speed of light. So here you can kind of see, here is the wavelength of one wave, and here is one that has a smaller wavelength. Okay, but what you'll notice is that when you have a bigger wavelength here, and here you have the smaller wavelength. When the wavelength is smaller here, the frequency, this is the important part here, the frequency is going to be greater. That's what this question is asking you here. Okay, what do you notice about the wavelength and frequency? Okay, the bigger the wavelength, so the bigger the wavelength, the smaller the frequency. We see that here. Okay, and then in this one has a smaller wavelength, and if the waves are smaller, of course, more waves can pass by every second because there's less of a wave to pass by. So in this one we see that the smaller the wavelength, the bigger the frequency. Okay, and that's a relationship that we're going to look at in more detail tomorrow, that when the wavelength is big, like a radio wave, there's not as many waves that pass by every second because it's a bigger wave. Okay, because remember, they're all traveling at the speed of light. When the wavelength is smaller, though, when you're up in the X-rays or even the visible light spectrum, more waves can pass by every second because the length of that wave is smaller, so therefore the frequency is going to be bigger. Okay, the amplitude is basically how tall the wave is. We don't really care about that. Okay, we're not going to use amplitude at all. So here you can see that notice that the distance here is the same. The amplitude we don't care about. But notice if the wavelength is the same, then the frequency is going to be the same. So these two would have the same frequency. Okay? And that's an introduction there to the electromagnetic spectrum.